So we'll get started. So this is OH in all its glory. If you're into combustion chemistry, combustion diagnostics, OH is an important thing to try to measure. In order to measure, you need laser equipment, but you also need to understand the spectroscopy. Oftentimes, you're just copying what someone else has done, but this is the basis of how you would pick, how you calculate the spectrum and pick transitions and interpret them. So this is a plot of the energy level structure for the x2 pi to A2 sigma system. So we use the word system when we change electronic states. All the lines that connect to those two electronic states are part of a system. Within the system, we have bands in which we have specified vibrational levels, upper and lower. And within each band, we have branches that correspond to the different rotational states. Now list what we have. N double prime of 13. We just picked N double prime of 13. What are the possible values of J? Well, J can be N minus a half and N plus a half. So J can be 13 and a half or it can be 12 and a half. Furthermore, because of lambda doubling, each one of those J states can either be a C or a D. C is always the higher one. So lambda is non-zero, therefore we have lambda doubling. We have a 2, which means we're going to have two combinations of J and N. So it's not enough for me to tell you or you to tell me J of 13. If I want to find a state, a specific energy level, I've got to specify J and I've got to specify C or D. What does that mean? That means that for a given N, there are 4 states. Finally, when I get to that level, there's no more splitting, and the degeneracy in that state will be 2J plus 1. Okay, that characterizes the lower level of this electronic transition. What about the possibilities for absorption? What are the possible upper states that we can connect? Over here now we've got possible values of, now the upper state is a 2 sigma. What does that mean? Lambda is 0. Well, that's good. That means there's no lambda doubling in these lines, of these states. But I still have to recognize that there's a spin of a half, and so I'm going to have, in the notation we had before, J can be N plus or minus a half. So for a given N, let's see, here's L N of 12. I can have 11 and a half, or I can go over here and I can have a 12 and a half. So if I think about all of these, if I think about these states, I can ask, what are the allowed transitions? Now I've got to start paying attention to this column called parity, P. There's rules that tell me that the C is a plus and the D is a minus for this odd value of N. So I can assign a plus and a minus, and I can assign a minus and a plus. Exactly how you do that, you just have to follow a rule. But the fact is, each of these 4 states has a unique value of the parity and the C or the D and the J and the N. So there's 4 states for given N. Each one of those then has allowed transition. So for example, over here, where I have N of 13 and I have J of 13 and a half, I might consider where can I go that will have a delta J of 1. That would be an R branch transition. If I go up here, I can find that from this state, which is a parity of a minus, but there's 2 states with the same J. But if I look up here, I've got to find places where I can end up on an opposite parity. So the minus parity can go to a plus parity where I've changed both N and J by 1. If I look around, I'll find that there's no place else for me to go with a delta J of 1. Now, if I look, for example, to see, can I have a delta J of 0, Q branch? You can't find one. But I can find one from this plus. Now I'm going to go from 13 to 13, 13 and a half to 13 and a half, and I've changed parity if I go from this level right here. That's a plus to a minus. So even though I've drawn all the possibilities up here for which you can have delta J's of plus or minus 1 or 0, recognizing they're the strong ones. So what does that mean? That means from a given n down here, I have 3 strongly allowed, meaning P, Q, and R, transitions that are possible. I can go from here with a P, I can go from here with an R, I can go from here with a Q. And over on this side, I can play the same game. From each one of these states, I can ask what are my possible P, Q, and R transitions, and I can find them. They have to change parity, and if I change J by 1, I get an R branch. So that's R. Now, you'll also notice that I'm calling this quantity here alpha. Have I introduced this yet? I'm not sure I've introduced this yet. The subscript, this 2 corresponds to the fact that this is the J is n minus. Remember I have the F1, F2, F3? Yeah, okay. So F1, this is the F1 because J is n plus a half. Over here is the F2 because J is n minus a half. So all of these are 1s over here, and these are 2s. The notation here for alpha and beta. Alpha is the corresponding number for the upper state, and beta is the corresponding number for the lower state. So it's J of n plus a half, n minus a half. So over here I have the same thing. J is n minus a half. The 2 tells me this is J n minus a half. The 1 tells me this is J. This is a way of putting everything down. So when you're all through, you find that there are 6 strongly allowed, meaning P, Q, or R transitions that can be found. These diagonal lines correspond to the fact that you can also have weak satellite bands in which the numbers, the subscript numbers change. I can go from a 1 and a 2 here. So when they're weak, but they're possible. So there's 6 strong lines from a given n. Or if you want to think about it, there are, therefore there's going to be that many number of branches to consider. So that's all because of lambda doubling. If the lambda doubling hadn't been there, we'd have a much simpler picture. So what have we learned? We got to, in this system, in which lambda changes, spin is always maintained. Spin is always maintained. But there's no lambda doubling up here, but there is lambda doubling down here. You have to change parity, and you have to put the parities on this list in order to figure out where you can go. All of that leads me to plot the diagram that I showed you on Monday of a line strength plot in centimeters to minus 2 per atmosphere versus wavelength. So this is the wavelength that separates these 2 electronic states, 2 pi and 2 sigma. These are lines, now because these line strengths depend upon temperature, I've done this at 1 temperature. And I've done this for 1 vibrational band. If I would do this for 1, 0 or any other combination, I'd get another set of lines, but they wouldn't be as strong. So I know that the 0, 0 band is the strongest band. I know this from the Frank-Condon factors. So once I fix the band, I fix the electronic transition, I fix the band, I fix the temperature, I can calculate the strengths of all these lines and their positions. So this is position information and strength information. Almost all the way to where I have to go to do a quantitative measurement. So what do we see here? We see that the Q1 is a little stronger than the Q2. And the Q1 is roughly twice as strong as the R1. That's just saying that delta J of 0 lines for this molecule are about twice as strong as the delta J of 1. And if you look in here, they're a little harder to see, but P1 is in here also. So it's better to study, if you want a stronger absorption, we now use these lines right here. Historically, for laser reasons, we use these lines right here for 20 plus years. In the last year, we've begun to use these because the line strengths are twice as big and we can detect lower levels of OH in an experiment. So it took a while to get here. This is lecture 8, I guess. But now you understand It's all about line positions and strengths. How do you calculate the line positions or interpret the line? Maybe you're reading a paper and you want to emulate what this person did here. You use the Q18 line, you know the wavelength, tune your laser there, make sure you're at the center of the line, whatever you're going to do. So you may not have to repeat any of these calculations. You may just want to copy what somebody else has done. But you'll have to understand how the line strength changes with T. And go back to the equations that I've shown you. Okay, so I'm going to go through the steps that are required to do a quantitative absorption coefficient calculation. First step, you have to identify and calculate these energy levels. And the hard part is the rotational part. You have to decide on the allowed transitions. You have to introduce what we'll call the transition notation, more notation. We'll have to decide what oscillator strengths to use, which means we have to face up to these Hahn-London factors. We have to calculate the Boltzmann fraction, the line shape function, and we're done. Okay. So everything, line positions are based upon differences between energies. So we take the energy of the internal states. Depends upon the electronics, the vibrational, and the J. And now within J, there may be some splitting that we have to take into account. We take advantage of what's called this Oppenheimer approximation, which says that we can write the vibrational energy without consideration of the other components. So where do we get these numbers? You would go to, say, Hertzberg as an example, and you'd look up and you'd find this row here, for example, for the A2 sigma plus state of OH. There's the electronic energy, 32,000 wave numbers. There's the vibrational frequency, 3,184 mega EXE. And then if I went to the ground state, x2 pi, here we are, term energy 0. So you go to a tabulation like this, and you immediately have T, omega, and omega EXE, which are, you immediately have this term, you immediately have this term. The trouble is always right here. How do we deal with J? And that's what we talked about this morning. How do you bring into account the fact that the total angular momentum J depends upon the nuclear angular momentum N, as well as the spin and the spin-orbit coupling. So that means that for a given J, there's 4 states. Enough. So this F of J has got the complexity in it. Now the upper state, if we believed in the Hund's case models, the upper state is the case where the lambda is 0 and the spin is a half. By the way, spin is almost always conserved. So the transitions we care about are almost always ones where the superscript is the same. It's the lambda value that can change. The A tells me this is the first excited state with a spin of a half. This is the lowest energy state, is X, term energy 0. Now there are other electronic states. There's B's and C's and D's that are higher and higher and higher up, which means the wavelengths are going to get shorter and shorter and shorter, and you may or may not want to use those. And if they're higher, that means the wavelength has to be shorter, and then once you push down to, say, 200 nanometers, you enter the vacuum ultraviolet, and you can't propagate light through the air. So there's a real reason why we tend to work with wavelengths longer than 200 nanometers in the laboratory. So this is a commonly used way of studying OH. It would correspond, if you looked at this, you would say this must be Hund's case B, because spin is a half, but lambda is a 0. But OH is a hydride, and whenever you have a light H in the molecule, it doesn't like to follow rules very well. So there's situations they don't follow the model as well as we'd like. Now what we have a case is because lambda is 0, that means that the sigma and the omega are not rigorously defined. That's this model right here. So there's no more omega out here. So we have now this case where J is n plus a half and n minus a half. There's 2 values of J for a given n. We call that subscript 1 and subscript 2. So F sub 1, J is n plus a half. F2 is J equals n minus a half. So now that says that if you give me n, I can recognize, and I know what J is. The only thing left is the lambda doubling to worry about. Now, what about OH? The problem with OH is that it looks like Hund's case B. It looks like this. It means that n can be 0, 1, 2, s is a half, j is n plus or minus a half, and here's our F1 notation, and which we write it this way. So you'll see that the state that we're considering might be written f sub 1 of n, or sometimes it's written f of 1 of j. That will tell me what level we're talking about. If you tell me, if this says f1 of 7, I know that j is 7.5. If you tell me that j, I can solve for n. Well, how do I know whether this expression f is written, when I say number, f1, f1, 7, how do I know whether that's n or j? Well, I know immediately because j is not equal to n. It's either plus or minus a half. So if you see an integer, here, it's n. If you see a half integer here, it's j. So that's one little trick to keep track of. So now all you really need are the energy level expressions, which you might take out of Hertzberg. Now let's look at the upper state first, because the upper state's a little simpler. Remember, you have to have energy level expressions for the upper state and for the lower state, and you take the difference. The upper state, lambda 0 spin is a half. So we immediately use the F1, F2 expressions that come. Here's the distortion term, which you can forget right now. So there's B sub V, which you're familiar with, n plus 1. That used to be J in the rigid rotor model, but now we have to call it n because we have to also add in the electrons. And so here's the additive term for the J equals n plus a half versus J equals n minus a half, plus, minus, plus, minus. So this is, and the splitting constant is about 0.1. So that just says that the F1 of 7 and say the F2 of 7 are split by about 0.2 wave numbers. It's actually a slightly V-dependent number, gamma sub B. So for the upper state, where we have the simple Hund's case, it's a pretty simple expressions if you just don't pay attention to this. But these numbers are in the literature. So that's not too bad. These are the energy level expressions for a specific n and j. That's all you need to know because there's no lambda doubling. Now, you also have to know the rule for how you specify the parity, but that's just a rule. So basically, all that's saying is if you have n of 2, j can be either 2.5 or 1.5. There's the F1 because j is n plus a half. F2, j is equal to n minus a half. And there's a rule that tells me that for this even value of n, these both have parity of plus. And now when I go to an odd number of n, I'm going to have a parity of minus. So for every n, there are two states split by this gamma term, two gamma terms. Each one has either a plus or minus. So the upper state isn't that bad. It's the lower state that's the tricky one. So now the ground state, why is it tricky? Because lambda is 1. So you'd like to think that this is Hund's case A, because it's the symmetric top model. We need lambda and sigma. It should be a Hund's case A, and it is a Hund's case A, an approximation. But because it's a hydride, meaning you got an H on one end, it doesn't follow the rules as well as we'd like. So it turns out that OH acts like Hund's case A when n is small, but it seems to transition to Hund's case B when n is big. How do we know that? Well, they look at the spectrum. You look at the spectrum and see the lines, what model works. And what happens is that for OH, it's called intermediate. It kind of transitions from A to B, so there's equations for that case too that are in the literature. So at large n, what happens is that the angular momentum of the electrons couples more to n than it does to S. So then S decouples from the A-axis. So there's a physical explanation for this that comes into play. But the bottom line is all you care about, what are the equations for the energy levels? Here they are. These are the equations built by other people that apply to OH. the term that we're used to, j plus 1 squared, lambda squared, this is kind of like the symmetric top term now, plus some correction terms. Oh, forget the d, those are the distortion terms. What's this? What's y? Well, y is this a over b that I introduced earlier. And now y here, here's the rotational constant. And you'd like to think that a is essentially determined by the moment of inertia. But the problem is that for OH, it's a negative number. And that's because it has this inverted character. So it's like a moment of inertia term, but it's got a negative number. And the only thing we care about is that means that F1 of n is lower than F2. That means it's inverted. But these expressions exist. They're known. You look up the values, and you're good to go. So now you have, well, this is just a reminder that when n is small, you can look at these equations and convince yourself it's equivalent to a symmetric top with spin splitting lambda a that I introduced earlier. Lambda a, remember it's a lambda sigma, but the sigma is one here. Is that right? Why do spin splitting is because there's a 2 factor in the s and it cancels out and gives me a 1 here. Okay, so it behaves like we think at low n, but it transitions to be b at high n. But these equations, I think I've shown you in the bottom, this is probably in your handout too. I think the handout in my lecture notes are about the same. This is just to help you see that this is true. In the end, all you care about is this expression. But if you want to understand it, you have to ask, does it behave the way you expect for small n and for big N? And that's down here. Okay, so here we are. Because here's F1 and here's F2. So this is n. So let's say n of 2. J can be 2.5 or 3.5. Here's 5.5, here's 2.5, and here's 3.5. Because it's inverted, the 3 has higher than the 5. That's okay. So these are the F1s, and these are the F2s, and that corresponds to the J of 3 halves and omega. Excuse me, omega of 3 halves, omega of 1 half. Now the problem is, if you want to try to understand these numbers, how does this come out? How does this square with my simple model for the spin orbit coupling, where I look up A in the tables and I find out it's a minus 140, which means this spacing right here should be 140. But when you do it for OH, based upon measured spectra, it's about 130. It means it's already drifting away from being the Hund's case. If you take this simple model, you should get 140. But I put all this stuff in my notes so that you can attempt to go. I had to do this myself. You have to kind of force yourself to go through this to see, do I really understand these equations? And so the intermediate equations. If you look at it the other way, if you look at from the symmetric top point of view, f of j should be j plus 1, a minus b. This is the symmetric top term. And if you evaluate this, it should be the actual space. The spacing should be lower by twice. It should be 316. But when you measure this difference right here, it turns out to be about 188. All that's saying is that the energy level expressions I gave you are correct, but when you try to approach them in the limits of small n and big N, the OH is transitions so fast that it's almost always in the intermediate case. So all of this is if you're trying to figure out, do you understand these equations? You're just going to use them. But okay, now the additional complication is I've got to do the lambda doubling. So I've got a j of 2, that means I can have, n of 2, j of 5 halves and 3 halves, but I got to have c and d. C is always the high one, and I have to sign the parities. So there's a rule for assigning these parities. So where are we right now? If you accept the energy level expressions for the lower state and the energy level expressions for the upper state, and you look and see which transitions are allowed, you're essentially done. You take the differences, and those are the wavelengths. In the literature, people, again, use they use compact notation. So if you wanted to describe exactly what you're doing, you would say that you're working in the X to A band, the X2 pi to A2 sigma band. Excuse me, I didn't say that right either. The X2 pi to A2 sigma system, and the V double prime to V prime band. And now this is how we describe exactly which transition within that band are we talking about. And this notation is all about delta J, really. But we have to recognize that because of this system, we can have different answers for N and J, depending how you write this. So this expression here, where the parentheses are either N or J, and you can tell if it's an integer, it's N. If it's half integer, it's J. And this is an X. This is delta J. That's the most important part. This is delta Y, delta N rather. And the alpha beta tells me which value of I I'm using. There's an I of 1 and I of 2. F1 means I is 1 here. The J is N plus a half. 2 means that J is N minus a half. But you've got to do this for the upper state and the lower state. So if I found, for example, this right here, that would tell me that they're talking about transition between, I'm missing the integer here, but I'm looking at transitions with a delta J of 1, delta N of 2, remember OP QRS, 2, and I'm going from F2 to F1. So everything's there, you just have to decide what it means. However, when delta J and delta N differ, they're weaker, and those are called the satellite bands. And so frequently, you don't see this notation here because that's suppressed. This Y is suppressed when delta N equals delta J, which are the strongest lines. Similarly, when beta and alpha are equal, that's suppressed. So frequently, you'll just see something like this. You'll just see R1 of 7. So what does that mean? Delta J of 1 means delta N of 1. And it means that you're in the F1 manifold, and it tells you that N is 7, because it's an integer, not a half integer. So these are the strong ones, and so that complicated notation often degenerates down to something simple. We have to remember to change parity once we've assigned it. We have to recognize delta J can be 0 plus or minus 1. It turns out that for this molecule, you can't have 0 to 0. So we're back to this thing. So this is the diagram that I'm trying to explain. So once you pick N, there's two values of J. And this is the J equals N minus a half. This is the J equals N plus a half. I assign the parity. C is always higher than D. I do the same thing up here, and I find the matches. And so these ones across here are the so-called satellites in which alpha and beta differ. They're weaker, but they're there. Double spin split state. What message I was going to try to give you. Maybe I was just trying to add some more text down here. How big are these splittings? If you look at the equations, you can see what the differences are in wave numbers. Oh, here's the case. Lambda, for N of 10, the lambda doubling turns out to be about 4 wave numbers. That's a big number. You can easily see 4 wave numbers. If the upper state had lambda doubling, we would have twice as many lines. So thank goodness the upper state is not lambda doubled. If we'd have been lucky enough to study a case that was not lambda doubled, namely X2 sigma to A2 sigma, see how simple it would be now? We'd have to only deal with the fact that we have F1 and F2. Whenever you have lambda non-zero, which would be here, you'd see pi. You have trouble. If you're lucky enough to see sigma, it's pretty simple. There's no lambda doubling. And now if you see a 2, you still have to worry about the spin. So that just means J is N plus a half and N minus a half. So what you need to keep in mind right now is there are, if you tell me J, I know there are 4 states with that J. 4 states. Therefore, there's going to be 4 lines with that same value of J. And all of this comes into play when we do the Boltzmann fraction. So remember where we're headed. We want the absorption coefficient. Depends on some constants, the number density in the absorbing state, and the oscillator strength for the transition we want to study. The specific transition we want to study, induced emission term, line shape term. This comes to us from this Boltzmann relation that says it's the total number density of the species and the Boltzmann fraction in that state. We're going to try to do this. How do we evaluate the parameters we need, which is the oscillator strength and the Boltzmann fraction right here? How do we do that? And if you sum the Boltzmann fraction over all states, what should you get? 1. So this is how you kind of check yourself. Have I defined my fractions such that if I sum over all of the states, I get 1? Remember, state is the energy level for which the remaining degeneracy is 2J plus 1, which I can't get rid of unless I have a strong field. We don't have that. Okay, so we want the oscillator strength that goes from one specific state to one specific state, where I mean state. And it's written as the product of the electronic and the vibrational and the Hanson-London factor for rotation. The good news is that this combination is often combined together into the band oscillator strength, and it's just a number. So for example, we often use this band right here. So the number is just essentially 0.001. Notice that the oscillator strength for a same lower state, the upper state of 1, is down by about a factor of 4. Where'd that come from? The Frank-Condon factors. So those are just numbers that we have to accept based upon experiments. These things are defined in a way that's supposed to make life simple. The sum of the Frank-Condon factors for all of the possible V primes from a given initial V double prime is 1. So wherever you are, you have to go to one of the upper vibrational levels, and the relative probabilities add to 1. Now, similarly, if you ask, if I'm in a given J double prime, what are all the possibilities going up? You'd like to say that the sum of the relative probabilities would be 1. But you have to remember that there's 4 states with J double prime. And so there's this factor 4 that keeps running around. This is the Kronecker delta is 1 when lambda is 0, but it's 2 otherwise. So we have a pi state, so that sigma is 2s plus 1 is a 2. So there's this factor 4 that's really just keeping track of the fact that there's 4 states for every specific J double prime. So when you sum these factors, you're going to get this 4. But you also get the 2J double prime plus 1, the degeneracy you can't remove. But if you remember, these Hanson-London factors are normalized by that number, and so they're going to come out to 1 also. Here's an interesting problem. Where did we get the oscillator strength, the electronic oscillator strength, or the F00? People have been measuring it for nearly 100 years. The interesting thing to me is that the best value is pretty close to the one that was determined in 1938. And different people have gotten some quite different answers. Marshall Lapp was a contemporary of mine, a friend of mine. So it was hard experiments. I would say this is kind of an old table. I'd say that we think we know it within maybe 3% now. Maybe probably 3%. Now, where do you get? So you get the band oscillator strengths by picking it from the literature. Where do we get the Hanson-London factors? Well, we get them from tables. And here's the Hanson-London factor, Sj double prime, always in its normalized form. Just remember the expression I had for S had a 2J double prime plus 1 in there. And the way they're normalized is such that, well, here's a P1 of 1.5. That means, so I've got the P1, the 1 tells me that J is n plus a half. The fact that it's a 1.5 tells me that this is a J, not an N. And here's my normalized Hanson-London factor, 0.56. And if I add up all the ones from that J of the 1 type, I get 2. And if I add up all these with the 2 type, I get a 2. And the sum is a 4. So these things always add up to 4 because there's 4 states for a given n, a given j. So it all makes sense if you just kind of stick with it. So regardless of the j, here's the j of 2.5. So there are, you might say, well, there must be 6 transitions for that given j. If I neglect the satellite lines, that's true. But the satellite lines are included here. So whenever you see a change, I put in the satellites. The sum of those things has to be 4. So you find these tables exist, and so you get the band oscillator strength, you get the Hanson factor, and you're almost there. So remember, we want to find, if the Boltzmann fraction means we want to know the Boltzmann fraction in a state. State is that for which the remaining degeneracy is 2g double prime plus 1. That means we've got a state. So in general, here's our Boltzmann distribution. The Boltzmann fraction in a state is the degeneracy, e to the minus energy over kT divided by q. And you just have to be really careful that you keep these numbers so that they add up properly. And we use the Born-Oppenheimer approximation that says we can separate these partition functions into the electronic, vibrational, and rotational. In the electronic mode, degeneracy is basically the number of states, the number of states with the same j. And that's why I end up with this factor of 4 here. That's where you have to decide where you put this factor of 4. And it's usually put here. The degeneracy in the ground state, which is the 2 pi state, is 4. What's the electronic degeneracy in the 2 sigma state? 2. They don't have lambda doubling. So the electronic degeneracy appears. And why do we care? Because the partition function depends upon the summation over states, which includes the degeneracies. On the other hand, the energy level spacing between the ground state and the upper state, electronic state, is so high. There's basically no population. Therefore, the partition function is going to be just a ground state degeneracy. So here we are. Given n is split into 2 j's, which is split into the c and the d. So there's 4 states. I call this a state. There's 4 states for every n, or 4 states for every j. And the summation of these factors for each state has to come out to 2j. That's the remaining degeneracy that we're not taking away, defined in a way that, and the Hanson factors are defined in a way that sums properly. So let's go back. The electronic, what's the Boltzmann fraction in this electronic energy level? Remember, we can take, assuming the energies are independent, we can take these exponentials and just sum them up, and the partition functions then are independent. So let's do the electronic first. What's the Boltzmann fraction in the ground electronic energy level? Well, it's the degeneracy, which is 2s plus 1 phi, et cetera. But when you do this, you find out that because of the electronic energy level spacing, you just get the vibrational mode is also simple. It's a diatomic molecule. It's the Boltzmann fraction in a given level. So if you're doing the 0-0 band, you want the Boltzmann fraction in V double prime of 0. The rotational one is the place where you have to be careful. Now what we do is we're going to combine what's the Boltzmann fraction in the rotational mode? Now I've got to be careful. I'm talking about n. Motion of the nuclei, because I have put the factor of 4 in the electronic. So this should look exactly like what we've seen before, except we're carrying along an f of n instead of the f of j that we're used to. The rotational partition function is still t over theta r when t. At this point here, we don't distinguish between f1 and f2. We just write f of n for this purpose. Okay, so what do we care about now? We care about the fraction in n, v, n, and j divided by the total. And in detail, this turns out to be a half. It's a half because n and j are about the same, and this 2s plus 1 is 2. Very small corrections to take care of here, but not enough to worry about. So in the end, we're now down to everything except the C and D, which comes in this parity thing. This is now going to be. So finally, we can combine everything and ask, what's the Boltzmann fraction in the absorbing state? Take the product of all these terms and write it down this way. Now, at this point, we usually put the F1 or F2 back in. What we find is that we're down to the fraction in a given state is just 1/4 of what you would have had with the rigid rotor. Why? Because there's 4 states with the same J. So and if you look at it that way, the Boltzmann fractions always sum to 1, as you'd expect. Now, we got one more little problem to deal with. Not really a problem. This is a history. This is history. If you're going to do an absorption experiment, there are really 2 types. You could do an experiment in which you have a monochromatic source, so that you have to take into account the line shape function. But until the invention of the laser, people didn't have monochromatic sources, and so they had spectrally broad sources. So if you have a narrowband source, then we're back to something that we're very familiar with right here, the line shape function. So if you measure the fractional transmission of light, and you know enough about the spectroscopic constants, including the collision broadening and so on, you can solve for the number density right away. But what if you don't have a spectrally narrow source? So let's look at an individual line. This solid line right here is the line shape function. But what if you have instrument broadening, meaning that you are trying to measure this with maybe a spectrometer? Perfect. When you go to scan across this line, you'll get something that looks wider because the instrument is broadened. So people recognized that they could deal with this. This is also because most people did emission in those days. So maybe you're looking at emission, or you're looking at scanning and doing a scan absorption experiment. But the apparent line would look like this. Because of conservation of energy, the area under the curves is correct. So in order to make a plot that can be compared between different laboratories, they took that area and they represented it as a rectangle, and they called that the equivalent width. So the arguments are, we think nature would have given us this if we had a perfect experiment. But because we have an imperfect experiment, we scan across and it looks wider. But by conservation of energy, all the energy was taken care of. So let's report it as the equivalent width, meaning this height is 1, and the width gives us the area. So we can conserve area and report it as the equivalent width for that particular transition. They called that the equivalent width. And people plotted the equivalent width that they observed. And now they want to compare it with simulations. So what is the equivalent width? It's the integral over frequency, apparent absorption, 1 minus the transmission. Apparent. Now, you would like to be able to compare that. You can get the equivalent width also from a correct model, which would be an integral actually over the spectroscopic theory we have. But because of the influence of the Voigt function, the impact of the equivalent of the instrument broadening, people started plotting tables that look like this. They're called curves of growth. This is all historical. You would probably never have to do this. People reported the curve of growth, and they calculated what the equivalent width would be, normalized equivalent width, normalized by the Doppler width. So you basically specify the transition you want to study, you take the spectroscopic parameters, and you calculate the equivalent width as a function of the Voigt parameter A. Then you ask, if you know, so if you measure the equivalent width and you know A, you're done. But, so the bottom line is that people didn't have lasers, and they reported their results in terms of equivalent width, and for comparison with theory, they used curves of growth. All of that's changed. That was the way it was until 1980 or so. You're saved all of this agony. I want to give you an example calculation for a particular transition. So let's say I've decided that the Q19 is a good one, and it is. This is in the X to A system. System then is all the transitions between these two electronic states. The band, 0, 0, for all the lines then in the V double prime of 0 and the V prime of 0. And the Q19 line. Q tells me that delta J, the fact there's no superscript tells me that delta J is 0 and delta N is 0. And the 1 tells me that I'm talking about the J equals N plus a half. The N tells me that it's N that I'm showing. So this is the Q19 line. This is the Q19 line in the 0, 0 band of the X to A system. It happens to be at a wavelength of 310 nanometers or a frequency of 32,000 wave numbers. And if I want to do this at 2,000 degrees, and if I did my calculation for the collision broadening, I would get a number of about 0.05. So what I'd like to know now is what is K as a function of the partial pressure of OH? So here's our expression. My constants, partial pressure, Boltzmann fraction. So basically, here's the line shape function, oscillator strength, Boltzmann fraction. So the question is, so I've just written in the constants for you. There's really three parts to this. What's F, what's 1, what's 2, and 3? Those are the three things I have to specify to get what I want. The oscillator strength, I take the table, I take the oscillator strength for the band, 0.096. I take this Honolulu factor from the table, put it together, and I get 9 times 10 to the minus 4. It's just a number. So as soon as I pick that transition, I've really got the oscillator strength. If I'm willing to accept the band oscillator strength and the Honolulu tables, I'm done. Line shape factor, you know how to do this. We calculate the Doppler width at that temperature. We calculate the collision width if we have the collision broadening. We go to the Voigt tables. This corresponds to an A of 0.17. We get the line shape function. It's a number, 3.13 centimeters. I got 1 and 2 are done. 3 is the place where you can make a mistake. Population fraction in the absorbing state. You can almost already get it. If I had to do this in the back of an envelope, I would say, hold it. N is 9. What's the rigid rotor Boltzmann fraction of 9 at 2,000? And divide it by 4. Because for every N, there's 4 states. So if you think about it that way, you're going to get a number that's essentially 1/4 of all these things. And when you're done, here's your Boltzmann fraction. 2% of the OH molecules at 2,000 degrees are in a specific state. So I really have everything I need. I put all these numbers together. I solve for K, and I get a number that's 177, in these units, it's 177 centimeters minus 1 per atmosphere, now times the partial pressure of this species A, OH, in atmospheres. So what would I do? If I measured the absorption, solve for K, actually I solve for take the negative log, find the absorbance, divide by L, I've got K. And now that I have this expression, I immediately can solve for the partial pressure of the species. So if I observed, we'll do it the other way around, I would observe that I'd get 59% absorption if I had a path length of 5 centimeters and if I had 1,000 ppm at 2,000 degrees. So that's what you want to look at. Gee, I could measure at 2,000 degrees, 1 atmosphere, path length of 5 centimeters, 2 inches. I would get 59% absorption at the center of the line if I had 1,000 ppm of OH. So that's really what you'd like to be able to do. Plan and execute an experiment to measure OH by absorption. The assumption is that it's uniform along that line of sight. It's never exactly true. But all of this, all that we've gone through, really boils down to, roughly, take 1/4 of the rigid rotor harmonic oscillator thing and then take the existing band oscillator strength. You're kind of done. There you'd be able to, if you executed these kind of calculations, you'd get back to, you could calculate this plot. Now you'll see here's the case where that's the satellite band. It's pretty wimpy. Here's the Q19 is up here somewhere. So you want to be near the peak. This is at 2,000 degrees, this curve. If I'm going to do an experiment at 2,000, I'd like to be using one of these lines to get the most absorption. What happens when I go down to 1,000 degrees? Well, it shifts down to lower N, so the peak transition will probably be one of these lines here. And the magnitude will be different because the line strength depends upon Boltzmann fraction and the temperature. When you go to lower temperatures, the Boltzmann fraction, the distribution gets narrower, and some of the values actually get higher. When you go to higher temperature, you're spread out over more and more states until the Boltzmann fraction goes down. We did it. So it looks hard, but usually when you're learning, you're just following what somebody else has done. You're just trying to understand it. Then you can take your own step. So with all this background, I want to start switching. I want to talk now about the title of this course is really Quantitative Laser Diagnostics, because laser absorption is quantitative. The linear method is quantitative. Some of the nonlinear methods are not so quantitative. So I'm going to talk about lasers and tunable diode laser absorption spectroscopy and fibers. We'll talk about the fundamentals and some applications in aero propulsion in the next hour. So let's see, how are we doing on time? We're actually doing fine.